So, hello everybody. My name is Peter Brecht. I'm the CEO here at PhotoSound Technologies. I want to take a minute to thank everybody for joining us for the webinar on photoacoustic monitoring of radiotherapy. We will have Samuel Toler, our test engineer. He's the one waving right now. He will briefly discuss the Legion amp. He gave a system overview. He will mention a couple of he will give us noise figures and the way it's operated. And then we will have a specific application which will be presented by Wei Zhang of the Optical Imaging Laboratory at the University of Michigan. It is about ionizing radiation and acoustical ultrasound dual-modality imaging using the Legion amp in combination with the Verisonics Vantage system. Throughout the presentations, if you have any questions, please use the question and answer form. You can also type into the chat. I will be monitoring both of those. Yeah, and with that, I want to say no further ado. I will hand it over to Sam to give us an introduction of what the Legion amp can do and what applications there are. Take it away, Sam.
All right. Thank you for the introduction, Peter. Ultrasound acquisition systems they typically function with a single frequency emission source, and then they receive on a targeted frequency generally. However, PA data, photoacoustic data, is by nature broadband and therefore requires a broadband acquisition system, oftentimes with very many channels of signal data coming in. Our Legion amp is a broadband analog front end. It's multi-channel, and it's made to interface with your typical ultrasound systems to help with photoacoustic data acquisition. And this would include the Verisonics system. And what this Legion amp will do is it will help to improve the signal to noise ratio as well as low frequency response. To accomplish this, our Legion amp, it's actually designed with a high input impedance rather than a frequently seen 50 ohm impedance for many other systems. This input impedance matters because what it effectively does with the capacitance of the probe is it forms a high pass filter, and you lose a lot of the lower frequency signal, and you end up with distortions, and you will lose out on some quantitative analysis and some spatial analysis as well for larger objects. The top of my slide here, I actually illustrate two different sized sources that are with two different probe capacitances and also two different input impedances. These signals should ideally be sawtooth waves, and you can see all of them have some distortion to different degrees based on this probe capacitance and the input impedance. On the left, we have a 0.1 millimeter diameter spherical source. On the right, we have a 10 millimeter diameter source. So with the smaller source, a lot of our signals are generally on the higher frequency range, so there's not as much distortion as compared to this 10 millimeter diameter source. And looking at the probe capacitances, red and blue are high capacitance, yellow is low capacitance. And on the right, it's the same. The higher capacitance probes typically do better, and we don't really necessarily have the comparison for the low capacitance 50 ohms on these graphs, but I will illustrate that on the next slide. But here you can see that with this larger source, we're losing out on a lot of this spatial analysis and this quantitative analysis here. As we get larger, because our lower frequency signal is lost due to this high pass filter effect from this input impedance. Our Legion amp is a 128 channels, and it is a flat 40 decibels of amplification. And on the bottom here, we just have an example, a strong source with a rather large blood vessel. And by the time the excitation generates ultrasound wave and it propagates to our transducer, you end up with about 55 pascals of pressure, and you have a total conversion of 1.1 millivolts using that transducer. This is actually the transducer for our Tritom fluorescence and photoacoustic imaging system. And then we amplify that with the Legion amp for 40 dB, and then the ADC's range is ideally 2 volts peak to peak on 12-bit resolution. And so our ADC ends up providing about 19 dB of amplification, with the amp providing that 40 dB. So it gives you a nice range to use your ADC on, and this is our lower end of our ADC gain. So you can go from up to like 50 dB, I believe, on our ADC. So with this strong source, you still have more sensitivity to work with here, thanks to the Legion amp giving you that extra boost. Okay, next slide. So here is a simplified block diagram of our probe model with the input impedance modeled here in this high pass filter box. This is all part of our amp and ADC system. And on the bottom of our graph here, we have an amplitude response. And this illustrates how you have a linear response with the Legion amp and our higher input impedance as compared to the 50 ohms with these lower input impedances. You can also compare high capacitance probes and low capacitance probes. So on this amplitude response, we have red and gray are both high input impedance. So it's nice and flat all the way down to very low frequencies. Conversely, with the low input impedance, the response is not nearly as linear, so your quantitative analysis won't be as accurate. And then also, with this higher input impedance, you can actually take advantage of these lower capacitance probes, especially with applications like you'll see next from Wei as he presents about X-ray or ionizing radiation excitation. You need lots of elements which are getting smaller and smaller and smaller, and then they won't be able to have as much capacitance. So it allows you to work with more and more elements and more channels. And on the bottom right, we have a noise density model as well. And it illustrates how you don't have as high of a noise floor due to the cutoff frequency with that high pass filter. You can see it's dropped down significantly. Of course, with the red higher capacitance probe, it does perform better compared to the lower capacitance probes, but you have much more range to work with here for your signal. So due to these factors, you're boosting your signal to noise ratio, and you are also allowing yourself to do more quantitative and better spatial analysis. Okay, so here we have some noise measurements. This is just a quick demo that we set up. This is just a Legion amp, and it's a modular version that's for our Legion ADC. And on the left, it's totally unpowered. So you have a baseline understanding of what it looks like without any power going through. And on the right, you can see the baseline noise level with power through the Legion amp, as well as this test board that we have it connected to. There are a few little spikes here, and that's actually due to EMI pickup. And this EMI pickup is likely being picked up through the open QLC connector here. Another thing I'd like to point out is that the baseline noise level is around that of a 50 ohm resistor, which is 0.9 nanovolts per square hertz. So our reference voltage on this noise spectral density graph is 100 microvolts, and then you can see we're below the 10% mark here. All right, so to continue this quick noise demo, we illustrated the difference between no probe and with a probe, as well as the presence of my hand near the connector. My hand is acting as an antenna, as well as just me being nearby taking a picture. I'm still acting as an antenna and inducing some noise there. And that's what these spikes are. To my understanding and to our understanding, that's what we believe they are. On the right, you can see it's quite significant with this low range here, as well as 2, 3, and 4, which seem to be consistent between all of the graphs. Now, as soon as we connect the probe, we're shielding off our open-ended QLC connector. And now it is no longer affected by the presence of my hand. As you can see, there's little difference between the bottom left graph and the bottom right graph, despite the presence of my hand close by. There may be small hints of this lower frequency noise spike here, but that's quite negligible. So this probe, whenever it's connected, it has a certain cable length, and that's essentially acting as an antenna, and you're picking up noise due to that. And that length of that cable is very important as well, because that will adjust what frequency ranges of the EMI pickup you'll be able to receive. And we can get more details for that later if you'd like. We could email it to you directly. Just feel free to ask in the Q&A or in the chat. But yeah, that's that for noise. These are the two different options that we have for our Legion amp. On the left side is our modular OEM product version, where it has a DLM receptacle on top, and then there's a DLM plug on the bottom. It also has adjustable stands, so you can adjust the height of the Legion amp compared to the faceplate of whatever ADC you're connecting it to, so that you're not straining these connections. And on the right-hand side, we have a few different connector types on our preamps. We typically have the DLM 260 and QLC 260s available, and these connect to our Legion ADCs. So that's that. I think from here on out, I'm going to go ahead and let Wei present on his applications with ionizing radiation. And I believe you're muted right now, so go ahead and.
Okay.
All right.
So thank you, Peter and Sam, for introduction, and thank you for PhotoSound to provide the opportunity for us to share our research. So today I will talk about a novel technology, ionizing radiation acoustic and ultrasound dual modality image for real-time monitoring of radiotherapy. So this image technology is mostly related to the radiotherapy. So I will give a brief background about this part. So as you know, to us all, the radiation therapy is one of the common used modality for tumor control, and it has been shown very great treatment outcome. So actually, most of the radiation therapy is image-based. I see here we want to mention that we are targeting to the external beam radiation therapy. There's also some radiation therapy that was implant some radiation source inside the body, but that's a little bit different. Here is we are talking about the radiation generated by the linear accelerator. So those image technology are image-based. So before the treatment, patient will receive some spatial image like CT, PET, MRI, using this sophisticated image technology to locate the tumor target and also for the treatment planning. So during the therapy, the radiation source will be delivered as planning. But it's also a very challenging thing is that if you deliver as it is, there's no real-time feedback for the radiation dose delivered. So the total therapy is an offline therapy. Currently, it's still very challenging to online monitoring the radiation dose delivered so that we can optimize the treatment planning, which is also a very hot topic currently named adaptive radiation therapy. For offline therapy, there's several limitations, such as the positioning, actually, before the therapy, patient will do a treatment planning. At that time, patient will lie on the treatment bed so that it can use to locate the tumor. But every time, so for each treatment, it has several fractions, but which means like that the patient need to be under the therapy for several times, which has limited accuracy and reproducibility for positioning, and it may be very difficult to place the patient in the same position as a planning. Also, during the therapy, even with the perfect positioning, the body motion and the respiratory motion can shift the organ by up to a few centimeters, which will totally reduce the treatment outcome. Another concern is the anatomy variation. So, different organ has different density, geometry, and property, which can affect the attenuation of the radiation beam. So those organs will attenuation the radiation beam before it reaches to the tumor target, which means that the total delivered dose may not exactly as the treatment planning. So all those limitations will reduce the treatment outcome. But also another thing is that if we can solve those limitations, it will highly improve the treatment efficiency. So here we are developing a novel technology with named ionizing radiation acoustic image iRAI. This technology using pulse ionizing radiation beam, which directly generated by a clinical linear accelerator and delivered to the target tissue. The acoustic wave will be generated based on thermoacoustic effect. It's similar like photoacoustic, which is commonly used. And another thing is that the transducer can detect the induced acoustic wave and reconstruct the initial acoustic pressure. So the initial acoustic pressure is proportional to the radiation dose delivery. So which means that we can use this technology using acoustic wave to resolve the radiation dose delivery. Another benefit of this technology is that we didn't involve any additional source. It's passive detection. So once the patient receives the radiation therapy, we can detect the acoustic wave to resolve the dose. So in order to develop this technology, we first develop a first generation iRAI dosimetry setup. So this is a really simple setup. It's like around 20 years ago, like photoacoustic image. So we are using a single element transducer with very large element size is around 1 inch in diameter and using 6 dB gains. And then the transducer will be rotated around the phantom to detect the radiation-induced acoustic signal. So the rotation will be driven by a motor so that it can do a tomography like a circle. So the exact setup is like the right finger. You can see that this setup is relatively big, and also we need a very big water tank to coupling so that we can detect the acoustic signal in a larger space. Also, so for this setup, it's mostly focused on phantom study. And you can see that our preamplifier is shielded really well, just in case we don't induce any noise from the radiation light source. So for using this prototype image system, we're evaluating the sensitivity of the dose measurement using ionizing radiation acoustic. So first, we are using the last cylinder, several different last cylinders embedded with a gelatin to simulate a tissue environment. And then we will using some different degree physical weights to attenuate the radiation dose so that we can have a different dose around the last cylinder direction. So according to the result, you can see that with 50 degree, 30 degree, and 45 degree weight, we are able to distinguish the radiation dose delivered in different cylinders. which means like that the system is able to detect the difference in delivered X-ray dose. Based on the calculation, a sensitivity about 2.9% was achieved using current data, which is lower than the clinical acceptable 3% variation. It demonstrates the iRAI radiation, iRAI for the dosimetry has its clinical value, so that we can use it to detect the radiation dose delivery. So another thing is that we don't only want to see the dose, we also want to see the accuracy of the radiation delivery, such as the beam and the target misalignment detection. So in this study, we aim to monitoring the misalignment of the beam against the target. So you can see that we are using a lever and embedded with the pseudo tumor. We assume that the radiation beam can cover the pseudo tumor, and also we design another experiment is to have the radiation beam shift to the pseudo tumor. And then we are using the ultrasound image. This is a non-integrated ultrasound system. We have a commercial ultrasound system. We try to combine with our first generation iRAI image system, so that we can use the iRAI to see the radiation delivery using the ultrasound to see the anatomical structure. And then we can do the image fusion to combine them together. So as you see, for the radiation dose image, we can see that even both on target and off target, we can see the radiation dose delivery. And combining with the ultrasound image acquired with a commercial device, we can see that the radiation beam is delivered to the target, where when we perform the radiation beam off the target, we can see that the radiation beam is misaligned with the target. So with this one, we can have a short conclusion that the iRAI image shows the field boundary and the interface between the different materials. And also the beam shape and the location can match with the desired target shown in ultrasound image. And also the misalignment of target beam and target also can be detected. So this is also demonstrates the feasibility of these technologies to detect the misalignment between the radiation beam and the target, which is a really important part for the radiation therapy. But as you know, for the first generation iRAI system, it has several limitations, such as time consumption. It takes around 20 minutes or even more for the data acquisition and the movement of the transducer. And also it needs a very large space, and the coupling media need to occupy the whole space, which makes it really difficult to perform experiment. Another thing is that when we try to detect the misalignment, the separate iRAI system and ultrasonic system only can provide the relatively precision. The image co-registration is relatively difficult. Sometimes it's just based, you have to do it by hand. I think there's no automatically registration. Also, another thing is that it's hard to perform the synchronization, because for most of the commercial ultrasound systems, it's unable to synchronize. So to solve this problem, we developed a second generation image system with the iRAI and ultrasound dual-modality image system. So we are using the commercial linear array and beneficial with the multi-channel ultrasound image platform. It's the VeriSonic system. So we can drive two probes together, and also we can use the same probe for both iRAI acquisition and ultrasound image, which means that the image is naturally co-registrated. In order to further improve, so for the previous study, we are using a relatively large size element to improve the signal to noise ratio. When we shift the commercial linear array, the element size will be much smaller. In order to further improve the sensitivity with such smaller element size, we are using the ranging amplifier to further improve the signal to noise ratio before the signal go to the ADC of the VeriSonic. So for this system, so this is the signal to noise ratio with the ranging amplifier. From the figure A is the signal of the linear array with the radiation source. You can see that even though we just purely place the linear array under the radiation environment, we still can get a huge noise. And with the radiation amplifier, around 60% of the dynamic range of the ADC was occupied. This is the reason that why we set the radiation amplifier for 40 dB, because we don't want the noise saturated. So we set the noise level to 60% of the dynamic range of the VeriSonic ADC. And with the radiation amplifier and 400 times average, we achieve a signal to noise ratio about 2 to 1. Although this is not a huge signal to noise ratio, but at least it made the radiation delivery detection feasible with both soft tissue phantom and in vivo. So with this dual modality system, we first perform a study to demonstrate its feasibility in real-time monitoring the misalignment with the soft tissue phantom. A rapid lever was used here. We have 2 transducers directly facing to the target. And then according to the image, you can see that the rapid lever was moved by a motor around the blue array. And with the movie, you can see that the radiation delivery can be directly seen with the iRAI image using the pseudo color, where the structural information of the phantom can be seen by ultrasound image. So with precisely control the timing sequence, the ultrasound image achieve a frame rate of 11 frames per second, while the iRAI, due to a large average, the frame rate is only 1.1 frames per second. But it demonstrates the dual modality image system is able to monitor the misalignment between the X-ray beam and the moving target in real time. So the in vitro study demonstrates the feasibility, but for further clinical translation, we still need to show an in vivo result. So in order to further demonstrate this concept, so we perform an in vivo study with rabbit and have the radiation being generated from a linear accelerator directly hit to the rabbit liver. And we have 2 transducers here. One transducer is for iRAI acquisition. Another transducer is for ultrasound image. We are combining 2 transducers so that we can fusion 2 images together. So during this study, you can see that we can use the ultrasound image to directly see the organ motion of the rabbit liver, and also the iRAI image, you can show the boundary of the radiation beam delivery. So in this situation, the misalignment between the radiation dose delivery and the anatomic structure can be clearly seen with this dual modality image system. But due to the using of a research linear accelerator platform whose repetition rate is much lower than a clinical device, the iRAI here is only achieve a frame rate of 0.09 frames per second. But it's the first time demonstrated the dual modality image system is able to monitor the misalignment between the radiation delivery and the moving target in quasi real-time manual in vivo. So although previous dual modality image system demonstrated the feasibility for animal experiment, but for considering the potential clinical translation and also considering the radiation dose delivery is always in 3D. So it's necessary to image the radiation delivery in 3D. So for the next generation iRAI, we propose to using a 2D matrix array, which enable the feasibility of the volume matrix image. And then in order to further improve the signal to noise ratio, 2 important parts is working. The first thing is that we have the central frequency of the 2D matrix array directly match the pulse, the radiation pulse spectrum, and also we have PhotoSound to develop an integrate 1024 channel preamplifier directly attached to the element so that we can avoid induce additional noise from cable like any other connectors. So in the future, we probably can show some results with the 2D matrix array for both animal and human in vivo. So in conclusion, so the iRAI system was established and able to image radiation delivered to soft tissue phantom, and the delivered dose can be measured by iRAI with a clinical acceptable sensitivity. Another thing is that the dual modality imaging system is able to monitor the misalignment between X-ray beam and the moving target in a quasi real-time manner, both in vitro and in vivo. Okay, so that's what I want to talk about regarding our research. Thank you.
Thank you, Wei. Currently, it looks like, there we go. All right.
Thank you, Wei. I mean, this is very exciting research, and I think the applications or the possibility of the applications are quite, to me, are quite staggering. I mean, you know, radiation therapy is known for their severe side effects, and I think using monitoring and exact dosimetry can help limiting the side effects of that quite a bit. We're doing a little bit of an audience poll that I would like to have right now. We just have about like a few questions, I think 3 in total. So I was wondering if you can do that. In the meantime, do you want to have the next slide? Then we can move. There will be a question and answer sections. I haven't seen anybody. Has anybody? So if you have any questions about the system, please ask them now in the question and answer section or in the chat. Sam, do you want to do the next slide? So in the meantime, I want to tell you a little bit about PhotoSound and other products that we have. PhotoSound itself was founded in 2015 by myself and 2 other guys, and we wanted to specialize on data acquisition systems as well as imaging systems based on photoacoustic and additional modalities. We have currently 3 main projects. One would be the Legion ADCs and with the amplifier, which is a multi-channel, true multi-channel streaming data acquisition system. With a base unit has 256 channels, and you can put up to 16 channels together. We realized that a lot of modalities require more than just than just photoacoustic alone. And by photoacoustic, I mean you can have any kind of pulse energy delivered, as Wei just explained. You know, it can be photons in terms of like photoacoustic, it can be X-rays, it can be RF for thermoacoustic. So our data acquisitions can handle that. We then built our Triton imaging system, which is a combination of photoacoustic imaging and fluorescence tomography. That's a tomographic system that you can see at the bottom right. And our latest product is called Moleculus, which is a combination of photoacoustic and ultrasound. The one difference that we have from other systems that make those, from our competitors that make those systems, is that we are primarily a photoacoustics company, so we actually understand the nature of photoacoustic signals very well and their broadband issue. So there's, for example, a Verisonics system has mostly ultrasound and has a narrowband detection area. So we believe that it doesn't quite accurately capture the broadband frequencies of that are generated during photoacoustic imaging. So I see that the poll was there. So let's see if there's any questions. and I don't see anything there. I have some earlier ones. In one of the questions was asked is like in a presentation is you know, you can can see the boundaries of the X-ray only. So why do you only see the boundary of the radiation dosimetry, even with the broad nature of our amplifier? Wei.
So actually, the limitation for only seeing the boundary is not only related to the signal-to-noise ratio. It's also related to the bandwidth of the transducer. So for most of the transducer, it has relatively limited bandwidth, which make it relatively difficult to detect the inner part, which has much lower frequency.
Okay.
It's also similar with photoacoustic. Yeah, we are currently learning something from photoacoustic in order to compensate this.
Does the pulse width of what is the pulse width, or what was the pulse duration of your linear acceleration?
So typically for linear accelerator, it's the pulse duration is mostly 4 microseconds for all the device. Okay. It's a little bit shift, but it's relatively not too much.
So there's one from Paul Carlson. Then he's asked, what are you doing to detect volumes, not just edges of large radiation fields?
That's a very good question. Actually, you know, currently for linear array, we're currently only detecting the boundary, and also we assume that with the linear array, with the beneficial from relatively large elements and higher signal-to-noise ratio, we are able to improve the reconstruction algorithm beneficial from some elements. We are able to resolve the inner part of the radiation dose delivery. But it's still currently still a little bit challenging.
Okay, and another question is, so you said the signal-to-noise ratio is only 2. Do you have any plans to reduce the signal-to-noise ratio even more? Are you planning to use like a source with more power, or which would make, are you planning to use higher gain or higher bit reactions? Higher bit, sampling rate.
So actually, the sampling rate itself won't improve the signal-to-noise ratio. The concern is that, for the radiation, for the radiation source, currently we are using the clinical device, which means like that. So it's a standard. We don't have too much compatibility to adjust the radiation source, because we want to make it compatible with clinical standard. If we change the pulse duration, maybe even change the treatment effect. Another thing is for the additional gain. The problem is that if we improve the gain, probably it will occupy the more of dynamic range of the ADC. So if the system noise itself is occupy most of the dynamic range, then average won't improve the signal-to-noise ratio, which is not great for the total image. I think the best solution is that maybe we can optimize in transducer side, have a relatively large element, higher sensitivity transducer, so that it can further improve the signal-to-noise ratio.
Okay, so I have another question from Paul Carson. Thanks for participating, and I can answer that myself. So the question was, did I understand that one of PhotoSound's devices allows pulse EXO as well as high gain preamps on the same transducer element? That is correct. That's our molecular system. The molecular system has 128 channels that can be switched between photoacoustic mode and pulse echo mode. There's a commercial system built in to moleculars in combination with our partner Telemet. So this one is basically switched between. So you have 128 channels that are switched between photoacoustic and ultrasound data acquisitions. You have another 128 channels that are pure ultrasound, that are pure photoacoustic, that you can then take images as well. So for something like exact or that you would have done, that would be something that you could have used to do both imaging at the same site. So you could do 256 channels of exact imaging and then 128 channels of ultrasound monitoring in a device that is about yay by yay by yay. Sam, you have one lying around anywhere close?
Unfortunately, it's in the other side of the office, so I would have to get up and take some time.
It's not that it's comparatively small. So I hope, Paul, that answered the question. We do have plans to, but that's about 2 years down the road, to build arbitrarily configurable pulsar with a bypass system. We call that our USB-A system, that is then scalable to like in a similar ways than our Legion amp is. So that means you could then arbitrarily program your ultrasound your ultrasound pulsar, and we're actually currently making our own chips with an ultrasound bypass, where you have the same high gain preamplifiers and everything can be done on a transducer element, but that's slated for the end of 2024. Then the last question that I see, and that's a question that I have too. So you said the pulse of your linear accelerator is 4 microseconds. So and usually the spectrum of the signal is a combination, of the pulse duration with the size of your object. So we see, a 1 centimeter object is a lot larger than has a lot lower frequency than a 0.1 centimeter object. So my question is like, so what is the spectrum that you expect from the combination of source and tumor targets? And the second, are you doing any specific modification to your linear array? Since I assume, or I believe, that the actual spectrum of the signal that you expect and the bandwidth of the array that you use in your ultrasound site are probably quite different.
Yes, that's a good question. Actually, for 4 microsecond pulse duration, it typically will generate an acoustic wave with the central frequency about 350 kilohertz. So, which means that it's lower than almost all the commercial linear array device. Actually, here we are using the P41. P41, the central frequency is, I think it's around 2 or 2.5, because it's from 1 megahertz to 4 megahertz. But actually, it also covers the lower to 100 kilohertz. So at this time point, you need to modulate the VeriSonic system. VeriSonic system has some compatibility so that you can modulate the band pass filter and the high pass filter. If you open all those filters to make it relatively broadband, you are able to detect the signal lower than 50 kilohertz, but due to the transducer bandwidth limitation, probably it's around 200 to, I think it's around 150 to 200, the lowest band frequency. Fortunately, the radiation-induced acoustic signal is within those ranges, so we are able to see something. But you know, the best choice is still you have a transducer customers decide to match the spectrum of the radiation-induced acoustic signal.
Okay, well, thank you. I have yet one more question from Paul Carson, and I think I think I can answer that as well.
Okay.
And Sam has maybe Sam can chime in. Let me read the question. As I understood it a few years ago, the switching between pulse echo and high gain systems added noise that limited the SNR of the high gain system. Have we found a solution? We believe we do. There's currently a patent pending on that. That's pretty much all I can say. I mean, it is currently operating in the molecular system. You are free to give that a try or submit more questions. We can probably do a couple of systems there, but we played around and we really thought about it in detail. And there are some issues with, you know, what is powered when, and that's about all the detail I want to get into it so far. Paul, if you have any questions like that, just contact us directly. And I think that is it. So thank you for everybody that participated in the things. I know for some of you guys, it's especially our Chinese participants, it must be quite early. I think our European listeners have it's probably in the middle of the day, so you don't have any much of those problems. If you have any questions, you can contact us at info@photosound.com. Do you want to go to the contact page, Sam?
Yes.
And then if you or more information is also on our website, and then other questions will be we have a presence on LinkedIn as well, where we regular post product updates and interesting results that have been done with our equipment that we produce. So with that, thank you everybody for joining. I hope you have a good rest of your day and make good choices.